Hey everybody, this is Chemical Reactions for AP Chemistry in 10 minutes or less. This video is meant as a refresher on some of the major topics in Unit 4 of the 2021 version of AP Chemistry. It's intended for students who have already learned this material and are starting to prep for the AP Chem exam. It's going to cover the following topics from the AP Chemistry course and exam description. You'll notice we'll save the acid-base titration stuff for another video. Let's get started. Now, before we start talking about chemical reactions specifically, let's first clarify that there's actually two different types of changes that chemistry could deal with. Of course, I'm talking about physical changes and chemical changes. For physical changes, we're going to look for things like cutting, breaking, bending, sawing, where you really don't ever get any new substances or new chemicals being created. In AP Chemistry, you've seen a lot of changes for more complex things, like maybe melting, where you've got some solid water that changes into liquid water. Of course, here this is only a physical change because it was water at the beginning and it's water at the end. What really makes this a physical change as opposed to other chemical changes is the fact that only intermolecular forces are broken here. For water, it's the hydrogen bonds between the molecules, but the stronger intramolecular bonds or covalent bonds, those actually stay intact. So that's why this stays the same substance and remains a physical change. We should mention that this deserves a little asterisk because there are some physical changes like dissolving, say dissolving of an ionic substance, where you actually do break an intramolecular force. That would be the ionic bond that breaks as the ions separate from each other. Even though that happens, it still would be considered a physical change when something dissolves. Now, that physical change would become a chemical change if the water molecules instead, say we started with some liquid water and after the change we now had hydrogen gas and oxygen gas. Those are completely new chemicals, making this a chemical change. Here we've got the intramolecular covalent bonds within H2O breaking, allowing those atoms to rearrange and form brand new substances, and you'll see that pattern with other chemical changes too. So that's really all we need to say about physical changes. The rest of Unit 4 and the rest of this video will focus on chemical changes, otherwise known as chemical reactions. First, we'll list out some common types of chemical reactions that you might come across, like synthesis reactions, where two elements combine to synthesize a new product, or the opposite of that, decomposition, where one type of reactant substance will break apart into smaller pieces. Or our replacement reactions, like single and double replacement, where elements will essentially trade places or replace one another to form new compounds in the products. Or my personal favorite, a combustion reaction, typically seen as combustion of hydrocarbons. Those are molecules made of carbon and hydrogen. When those types of molecules combust, you get the same two products every time, carbon dioxide and water, along with the release of a whole bunch of heat. So a lot of the chemical reactions that you come across will fall into one of those five categories. The weird part is that the AP Chemistry exam is actually more concerned with three other types of chemical reactions. Many of those are going to overlap with one or more of these five original types. These include acid-base reactions, where an acid and a base react together, and according to the Bronsted-Lowry definition, that acid will transfer a H+ ion or a proton to the base, leaving me with A-, or what is called the conjugate base, and then Hb+, or what is called the conjugate acid. Or precipitation reactions. For these, you'll notice two reactants, could be more than that, but typically two reactants, both that are aqueous, and one of the products is not soluble and ends up precipitating out of the solution as a solid. And lastly, redox reactions, where the reactants have certain oxidation numbers. Say A has an oxidation number of 0. Then in the products, if A has an oxidation number of +2, that indicates that electrons were transferred between A and B. You'll also see a change in the oxidation number of B, further indicating the transfer of electrons and telling you this is a redox reaction. Let's also mention something called net ionic equations. This is just a special format, or actually more accurate way to write the chemical equation that describes a chemical reaction. So here's the balanced chemical equation for the reaction of calcium carbonate solid with hydrochloric acid aqueous. Notice the phases these different substances exist in: solid, aqueous, aqueous, gas, and gas. To turn this into a net ionic equation, we need to take any substance that is aqueous, and if that substance in its aqueous form exists as separated cations and anions, we're going to write it that way in the chemical equation. So HCl is aqueous, and as a strong acid, it will dissociate into 2H pluses and 2 Cl minuses. Notice calcium carbonate would not get separated into ions. Even though it is ionic and made of cations and anions, it's not soluble, so it will not dissociate into separated ions in solution. That's why it had the little parenthesis S there in the first place, so we do not split that into ions in my equation. We'll have to do this for the products as well. Notice calcium chloride is also aqueous and ionic, so that will dissociate into Ca plus 2 and 2 chloride ions. Carbon dioxide gas and water vapor will not dissociate, of course, because they are gases, so their formulas remain written the same way. The next step is to simply notice that some of these ions actually don't change at all. That means they don't react. They're called spectator ions, and we want to remove them, essentially cross them out from the chemical equation, because they're really not part of the chemical reaction at all. Here, I notice that 2 Cl minuses are unchanged between the reactants and the products. I'm going to cross those out and then rewrite everything that's left over. That will make up the net ionic equation. So there's the final net ionic equation at the bottom of the screen. We've left out all the spectator ions that aren't changing and included only the atoms that actually react or change in some way. And finally, we've got what is perhaps the most important topic in the chemical reactions unit, called stoichiometry. This means calculating, or at least thinking about, the quantities of reactants compared to the quantities of products and how they change over the course of a reaction. Conceptually, stoichiometry is pretty simple. Let's imagine I've got this container full of some gases. These two little dots represent some H2 molecules, and the two larger circles represent some O2 molecules. I have 4 of each. And what I want to do is use the chemical equation that has been balanced with the coefficients 2, 1, and 2 to try and think about what this container will look like after the reaction is over, or when it can't happen anymore because I've run out of one of these reactants. So I can see from my balanced equation here that 2 H2s is going to combine with 1 O2. And I can maybe circle those to sort of keep track of that. So here's 2 H2s combining with 1 O2. And every time that happens, they're going to disappear. So they're going to go away. So I'm not going to show those in my product container anymore. And instead, they've turned into 2 waters. So I'll add in 2 water molecules as products of that particular combination. If I do that again, using up 2 more H2s and another O2, let's grab this set right here. Those are going to go away, producing 2 more water molecules. And you'll see that at this point, the reaction can't continue because there aren't any H2 molecules left. The whole process stops, even though there are still 2 O2 molecules left behind that I'd have to represent in the container. We've also just identified a concept called the limiting reactant or limiting reagent. Here, that would be the H2 since it ran out. We've also identified the excess reagent, the O2, since it's left over, and then of course my H2O as products. We'll close this video looking at the calculation side of this and how you might do a stoichiometry problem involving actual quantities instead of diagrams and pictures. My first tip is to always change any quantity into moles. That's because when we do stoichiometry calculations, as you're about to see, we have to use what's called a mole ratio from the chemical equation, and that's going to be easier to do if I've already converted all my quantities into moles. Once you've got your values converted into moles, then you will use the mole ratios from the balancing, like 2 moles of H2 for every 1 mole of O2. Lastly, remember that it's the limiting reagent that controls the reaction, like the H2 in this example over here. Once it ran out, I stopped making products and stopped using up oxygen. So the limiting reagent should always be your starting point for any stoichiometry calculation. So here's an example. Let's say I did this calcium carbonate and hydrochloric acid reaction as described over here, and I produced and collected a certain amount of water vapor, and I know that that quantity of water vapor was 7.2 grams. I'm going to take those grams and first convert them into moles using the molar mass of water, then use the mole ratio from the balanced chemical equation to solve for really the moles of anything else in that reaction. Let's say I wanted to know how many moles of HCl reacted. That mole ratio is 1 to 2. And lastly, it's common to convert that mole quantity into something else, maybe grams. This would finish the problem. I would do the math and come up with a final answer of 29.2 grams of HCl that reacted. And lastly, let's talk about finding the limiting reagent. Sometimes that's your task, is to be given some reactant quantities and you're asked to find which one will run out first. The first thing we need to do is make sure those reactant quantities are both in moles. If they're given to you in some other value, you're going to want to convert them over. Let's again say we're working with this calcium carbonate and hydrochloric acid reaction, and I found out that there's 0.15 moles of calcium carbonate and 0.52 moles of HCl. Next, we'll randomly pick one of those reactant mole quantities and use it to solve for how much of the other reactant would be needed to fully react with that quantity. Here's how it looks. Here you can see I've chosen to start with my 0.15 moles of CaCO3. You could just as easily start with the 0.52 moles of HCl. Once I've got that though, I'm going to simply do a mole ratio to solve for how many moles of HCl I would need to react with all 0.15 moles of calcium carbonate. That mole ratio is 1 to 2. This tells me that I would need 0.3 moles of HCl to react with that quantity of calcium carbonate. To find out what the limiting reagent is, I simply compare that amount to the amount of HCl that I actually have, which remember was 0.52 moles. I can see that if I have 0.52 moles of HCl and I'm only ever going to need 0.3 moles, I will not run out of HCl. In other words, HCl isn't the limiting reagent, it's the excess reagent. And there's only 2 reactants here, so if I know that the HCl is not going to run out first, that means the other one, the calcium carbonate, will run out first, and CaCO3 is my limiting reagent. So technically steps 1 and 2 are all you need to find the limiting reagent. I did add a step 3 just as a reminder that once you've identified calcium carbonate as the LR, you're going to want to use that 0.15 moles of CaCO3 as the starting point or the basis for any other stoichiometric calculations you do, because the limiting reagent is the one that controls the entire reaction. So we went a little bit over time for this one, but that does wrap it up for chemical reactions for AP Chemistry in 10-ish minutes or less. Thanks for watching.